Welcome to section 6.4. 6.4 is called the Fundamental Theorem of Calculus. This is the last of our really big important theorems with the EVT, IVT, MVT, and now FTC. You can guess this is pretty important because this is called the Fundamental Theorem of Calculus. It comes in two parts. This video is only going to focus on part one. We'll talk a little bit more about part one on Friday. And part two will also get discussed a tiny bit in this video, but we've actually already covered most of it. So the FTC first starts with a hypothesis that our function f must be continuous. Part one then says if capital F is the integral from a to x of f with a dummy variable of t, then the derivative of capital F with respect to x is our function in terms of x. This is really, really important because what this is saying is that integrals and derivatives are inverse operations of each other. This is what connects the fact that the last section we were able to start evaluating definite integrals using antiderivatives, is because integrals and derivatives are inverses of each other. An integral will undo a derivative, and a derivative undoes an integral. Part two is just saying that if capital F is my antiderivative, in other words, the integral of f, then the integral of f from a to b is capital F of b minus capital F of a. This is what we did last section. We're not going to spend a ton of time on part two. Most of what we'll be focusing in this section on is part one of the FTC. So again, FTC is saying if I have an integral where the x is actually my upper bound, a is a constant, the t in this is a dummy variable. It's just a placeholder until x can be plugged in. X is my true variable here. So capital F of x is the integral from some constant to x of f of t dt, where t is a dummy variable. Then the derivative of capital F with respect to x, not with respect to t or a, but with respect to x, will be the derivative of that integral. Well, that's actually just f of x. And all that's really happening here is we replace the dummy variable with what's in the upper bound, and then do the chain rule on the upper bound. Now this only works if x is the upper bound and a constant is in the lower bound. I will show in a moment here how you deal with it if x is not in the upper bound or if you have variables in both bounds. So for example, if we have the derivative with respect to x of the integral from 3 to x of t dt, well, the derivative cancels the integral, x replaces the dummy variable, and then times the derivative of x, which is just 1, so we just get x. If I look at the derivative with respect to x of the integral from -4 to x of 3t squared dt, well, again, x is in the upper bound, constant in the lower. Derivative cancels the integral, so x replaces my dummy variable, and then times the derivative of my upper bound, which is just 1 again. And so the derivative of this integral would be 3x squared. Getting a little more complicated here. Again, here, derivative of the integral with respect to x. X is the upper bound, constant in the lower. So derivative cancels the integral. X replaces the dummy variable times derivative of my upper bound, which is just 1. Here, derivative cancels integral. X is the upper bound, constant in the lower. So x is just going to replace my dummy variable times the derivative of my upper bound, which is 1 again. A little bit more interesting here is I'm doing derivative with respect to x, and I see x's are in the upper bound, constant in the lower, but now it's an x squared. So it's still set up in a way that I can do the derivative of the integral because x is in the upper bound, constant in the lower. So the derivative cancels the integral, but now it's not just x that replaces the dummy variable, it's the x squared, because that's my upper bound, is going to replace t. But then I have to do chain rule on the upper bound, so times the derivative of that upper bound. Similar here, I'm doing derivative of an integral, constant of -5 in the lower bound, and I have variables in the upper bound. So derivative will cancel the integral. The dummy variable t is going to be replaced by the 7x plus 1, whatever my upper bound is. But then I need to do the chain rule of the upper bound, which is 7. A little bit more complicated here. Uh, this is almost in a format I can do, in that I am doing derivative and integral, but my bounds are in the wrong place. I need the constant in the lower bound and the variable in the upper. Fortunately, we do have a property for this, which is our order of integration property. So I can switch the bounds, and then I just make this negative. So I'll have the negative derivative of the integral from 5 to x, instead of from x to 5, of 3t sine of t dt. So now it is in the proper order. Still have my negative here. Constant in the lower bound, x in the upper bound. Derivative will cancel the integral. So x just replaces my dummy variable. So I'll have -3x sine of x. The most complicated these get is if I have variables in both bounds. And what I need to do here is I'm going to have to actually use the additivity property to split my integral up into two pieces. So I'm still doing my derivative with respect to x, but now I'm going to split this up, and I'm going to say 2x is going to go, I'm going to start at 2x, and then I just need to pick a constant. It doesn't matter what the constant is. I usually just pick 0. It really doesn't matter what it is. But then, using additivity, I'm now going to go from 0 to my upper bound of x squared. So now I do have one of my integrals is in the proper format to do the derivative with constant in the lower, variable in the upper bound. But my first integral here, it's still not in the right order. I need to switch the bounds. So I'm going to do my order of integration property on that one. And now both integrals are set up with a constant in the lower bound, variables in the upper bound, and I can do my derivative. So derivative will cancel out the integral. So the 2x will replace the dummy variable, but then I need to remember to do my chain rule on the 2x. On my second integral, derivative cancels the integral, so x squared replaces the dummy variable. But I do need to do my chain rule on the x squared then. And there's the derivative.